Hi everybody, I'm coming to you from the beautiful downtown Dahlonega D2L studios, and I'm constructing for you an example of the chapter 6 inferential statistics chapter. And the reason, and I just want to try to give you an overview of how this chapter can help you understand the fundamentals of statistics. I hope I'll be successful in doing this. This is how it comes to us. When we take raw scores and get a data set, we end up with a frequency distribution that's all over the place. That frequency distribution is explained to us in tables where we have frequencies and cumulative percentages, and it's also exemplified for us in graphs. One of those graphs is typically shown to us in this type of way, wherein you have a set of raw scores here. The raw scores range from the minimum raw score down here to the maximum raw score up here. And frequently, when we compute the mean, that thing ends up somewhere in the middle. But if the distribution of scores is skewed in some kind of way, this would be a positively skewed distribution because most of the scores are down here below the mean. And a couple of scores are pulling the mean up in this direction. And so this is what happens with raw scores. We can't use a distribution like that to make inferences about the population, because if the population is not skewed like this, and our sample is, then we're not going to be able to make reasonable inferences about the population based on this sample. However, it might turn out that the distribution is negatively skewed, and again we have the mean right here somewhere reflecting the fact that it's got information about every score in it, but because some of these scores are way low and most of these scores are up here, then the mean is not showing us a very accurate situation. So what we want to do in that instance is somehow smooth out the distribution so that we can make inferences about them. How do we get that distribution we're talking about that's smoothed out? Well, in addition to the fact that it could be skewed positively or negatively, the distribution itself might not have very much variability in it, in which case it would look like this, where all the scores are very close to the mean. There's not very many scores far away from the mean. Additionally, it could be very spread out so that you've got scores, lots of scores down here and lots of scores up here, and the mean is not showing us very big thing. Okay, the difference here is this is a small standard deviation. This is a big standard deviation. And so how are we going to get that sample to give us inferences about the population when either it is skewed like this one here, positively, negatively skewed like this one here is, or has a small standard deviation like this one with a very tall crown, or it's spread out all over the place with a large standard deviation? Well, how we do that? The answer to that question is, how are we going to get this, be able to make inferences about the population based on this sample, is we use what they call in the book the sampling distribution, meaning the sampling distribution of means. So what they'll do is take a sample from the population and compute the mean. And then they'll pour the scores back in, take another sample, compute the mean. Then they'll do that 10,000 times. So you've got 10,000 sample means all out here showing us that we've got every possible sample from the population, and when we look at its distribution, it ends up looking like this cool thing here, which we call the normal curve. And therefore, this thing allows us to make inferences about the population based on data from the sample, because we pretend the sample looks like this. Well, how can we do that? Well, if the sample size is 100 or more, then we can make use of that large sample, 100 or more, for the purposes of making inferences about the population. We can do it with smaller samples too, but there's a trick to it. Anyway, that's a different topic altogether. What I'm doing now is showing you that the normal curve gives us the potential to make inferences about the population. And how does it do that? Because this normal curve up here we got from the sampling distribution of means shows up with fixed percentage points between each standard deviation. So although it may not in reality resemble the population, it does for our purposes because of this larger sample size, which we pretend is normally shaped, and the standard deviations, the percentage of scores between each standard deviation is fixed. We got 2% down below 2 standard deviations below the mean. Then we've got 13.5 standard deviations here, giving us 2 plus 13.5, 15% of the scores here. You add another 34% to that, and you end up with 50% of the scores falling below the mean. So all the standard deviations below the mean contain 50% of the scores, likewise 50% of the scores over here. You add another 34.13% of scores to that, and that gives you 85% of the scores. And up here, this gives us the ability to compute probabilities of getting a sample and make inferences by testing the null hypothesis. That's a very simple explanation of this thing, and I hope it has sorted you out a little bit. Please call me if you have any other questions about it. I'm just trying to make what could seem like a very complex textbook explanation of the inferential statistics a little bit simpler to understand. I hope I've done that. Give me a call if I haven't. I'll see you then. Bye-bye.